In Unit 6, I now want to talk about text indexing. That is the string matching problem in reverse, where we do pre-processing on the text and assume that the text is given, as opposed to pre-process the pattern. And this will turn the problem on its head. It will make very different solutions and trade-offs possible. And it's definitely one of the areas that has had a huge influence on practical applications, in particular in bioinformatics, where this is applied to whole genomes to search very quickly and efficiently for certain strings or certain patterns. And last not least, to find matches of small fragments in a larger genome. This is effectively what also many PCR tests build on partly. So you're probably all profiting from algorithms in this unit. With that advertisement, let's start into it. It's also one of my favorite topics in this class. It's beautiful, it's impactful, it's deep, and somewhat mind-boggling a little bit as well. But it's very approachable if you do it step by step. And then if you take a step back at the end, you see, wow, we built this amazing machinery that can do this, these magic tricks that seemed impossible at first. But you can do it step by step, and it falls into place at the end. It's just very enjoyable. I hope you agree at the end of this Unit 6. The overview of this unit is, I'll talk a little bit about the underlying problems that we address here. And then we'll talk about our main star in this unit, the suffix tree. That solves many of the problems, at least conceptually. We'll look at some of these in the applications. And then probably after Easter, we'll continue with how to construct suffix trees. And that will lead us through longest common extensions, which are used for some more applications. It'll lead us through suffix arrays and LCP arrays. And then the combination of these understandable linear time algorithms to construct suffix arrays will then lead to the final solution. If that sounds a little abstract, don't worry too much. We'll go there step by step. And as a first step, let's look at what this problem is all about. So what is text indexing? It's also sometimes called offline text search. We're still in the realm of the by now very familiar string matching. So we're trying to find a pattern in a text. And again, the pattern has length m, the text has length n. This is all exactly as it was in the previous 2 units. What has changed now is a bit the perspective. We think of the text to be fixed and the pattern to come, well, we think of the same text to be queried after many different patterns. And this is now moving the problem closer to a data structuring task. Instead of thinking about algorithms, how to do one-shot queries, you're given, here's a text, here's a pattern, now find the pattern in this text, or show that it doesn't occur. We think about, here's a text, you're given this up front, you can do your magic with it, and then afterwards I'll fire queries at you, one pattern at a time, and you have to tell me where it occurs in this text. Okay. You might know that this word index is used in many different places. It's really the index finger, right? Is also where this comes from. It's just pointing. Traditionally in books, you have an index at the end, a list of all the words or concepts, and they point back to positions in the long text in the book. So this is not different from that, but we will approach the problem in a slightly more general setting, as you will see. There's tons of applications that under the hood use text indexing in one way or another. Web search can be seen as exactly that. They usually don't have one contiguous text, but documents of smaller texts. You will see that this is essentially the same though. Dictionaries in the traditional sense, well, an English dictionary, you want to find a word quickly. You don't want to flip the book these days anymore. Same for other bigger databases, and as I mentioned, the bioinformatics applications. The traditional way to do this in books is an inverted index in the terminology of computer science. And this is simply instead of having the text where all the words are listed in the order they appear in the text, which, by the way, is how we want it if we want to read the book, an inverted index takes all the words that occur and maps that to the page in the book where they occur. And that could be several pages, usually. Okay. There's an assumption behind this, and this is also a limitation of the traditional indices in books. You only find in this index what someone cared to put into this index. And especially in printed books, you can't make the index arbitrarily big. And the underlying assumption here is that we only search for entire words. Sometimes this makes sense. For natural language text, this is often what you want. If you search for a word, it's often not so helpful if you report matches that are just within another word. And then this works fine. What we do for this is you're given the text, then you split it into words. For natural language, that's often clear how to do. You just split the text at white space. In practice, you want to go a little further using the fact that this is, say, an English text. You want to reduce words to their stem so that if someone searches for cats, if someone searches for a cat, he or she also finds occurrences of cats or other related forms. This is what users expect. But we will not dive into this part. Usually these are heuristics based on the language, and it's fairly well understood how to do this for English. It might depend on the language how well it works. What we still have to do is store a mapping from words to the list of occurrences. And this is now an algorithmic or a data structure question that you can make sense of already. And in a sense, this is just like a dictionary. So you have keys and you have values, right? The keys are your words. And the values are list of occurrences. Which you cannot see. The values is a list of occurrences of that string in the text. That is totally doable, but if you implement such a dictionary with a binary search tree, search would still take logarithmic time in the number of words that you store. Now, just give this a rough back-of-the-envelope calculation. If you were running a web service like Google Search the entire web, and you had a dependency on the size of the web in your search, guess how well that would work? That's definitely too slow in that scale of data. It might just be acceptable for some other applications, but it's definitely not the way to go in the general case. And the reason why this dictionary approach, if you use a binary search tree, so maybe this is worth noting, a binary search tree would work, but queries need log n time. And that can be too much. Okay. And how can we possibly improve upon this? We can make use of the fact that the keys are not arbitrary objects, but strings. And we can do more with strings than with arbitrary objects. And now I want to see if you know this term tries, spelled T-R-I-E. Just so that I know if I have to explain this or not. Again, yeah, I'm trying to make the answers a bit more energetic and not too dry, but yeah, it's totally fine if you haven't heard it. It's something that sometimes is taught in undergraduate algorithms or data structures classes in computer science. But then a third of you haven't ever gone through an undergrad in CS, and even those who have might not have seen tries in great detail. They're not in the total must-have of data structures, which is a shame, but that's what it is. Okay, we have our usual 25 almost. Okay, now we got it. So you see the results. It looks like we should definitely spend a little time on looking at what tries are. So what are tries? At the basic level, a trie is an efficient dictionary where the keys are strings. This is exactly what we need, right? We need a dictionary where our keys are the words in the text, and we can associate some value with that. The weird name, someone found it nifty to use retrieval to retrieve the keys and take this infix, this substring as the name. But then because tree from retrieval, that sounds like tree, like the tree. And well, I mean, it's not, at the end, a trie is a tree, but they didn't want it to sound like tree, otherwise people would be confused, so it's pronounced try. Well, that's what it is. It kind of gets it's stuck like this, and it's a short name. It's maybe not very logical, but that's maybe not too bad. It is a tree though. This is what I said here. It is a tree, but it's not a binary tree, and it's used in a slightly different form. Maybe I'll show you the example first. This is an example trie. There's a root node. This is like in binary trees. Now this one is binary, but that's because the alphabet is binary. And it's not entirely true because there's also this dollar. But I don't have a ternary node. I do have nodes with only a single child. In general, a trie node can have as many children as there are letters in the alphabet. In the basic version, a trie simply says, if you want to store a string BBA, you have to make sure that if you traverse the path from the root to this node, to this key, the labels of the edges spell BBA $, exactly the string that you store. That's in essence what a trie is. You make sure that every edge is labeled with a symbol, and if you read the edge labels as you walk down to a leaf, that gives you exactly the string that is written in the leaf. Now, there are a few catches and caveats. To make this work, we assume that the strings are prefix free. So that means no string is a prefix of some other string. If you had this, if there was a string that's a prefix of another one, it would end in the middle of the trie. And that's inconvenient for various reasons. You can handle this in different ways. The easiest is to say we assume that the strings are prefix free. And that's, for example, true if they all have the same length. Then no string of the same length can be a prefix of another string. Or if we append a special symbol and the convention here is to use this $sign. So again, you see things are dominated by Americans. We use this $sign always in this unit to mark an artificial end of file character. It's important that this character does not occur as a usual character in the alphabet. So if that ever happens, you have to find a different, make it a green dollar or whatever. The assumption is you start with strings over some alphabet, sigma, and then you add the $sign as a new one. And by making this the last character in every string, appending it to every string, you make sure that there's never a prefix. Never one of these is a prefix of another one, because that would mean the dollar occurs in the middle of some other string, and we didn't allow that. So here's some more systematically, what this example shows is here's a set of strings over the alphabet just A, B. So don't have this on the slide, but it's worth noting that the alphabet is just A and B. We appended to all the strings the $sign, and then we constructed this trie exactly by, well, every node here can have a child labeled A, labeled B, and labeled $. And say if we added another string here that's just $, we would indeed have this as a new leaf and a new node. And then you would have a ternary node where you have 3 children. Okay? Because the edges are labeled, it doesn't really matter in what order you draw them, but it's often convenient to be consistent. But that's not a must. Okay, I hope you have a somewhat better idea now what a trie is. I didn't talk about how to construct them or how to use them for searching much, but maybe you can imagine if you were to search for a string, you would just walk down the tree and follow the edge with the appropriate letter. If you ever reach a point where there is no node, where there is no such outgoing edge, say you look for BA, you traverse B, but then there is no A, then you already know there's no, this string is not part of the dictionary. And to insert something, you do the same thing. You walk down the tree as long as you can, and as soon as there's no further edge to follow, you simply add a new child to this node and give it this label. Okay. So much for that. Now let's see how much you were able to follow this. Here's a fairly long question, so I'll have to give you a little time to read this all. Basically, it's asking about the query time of a trie. You have a trie that stores n strings over the alphabet of just the Latin capital letters. Doesn't make a very big difference. So 26 letters. Each stored string has exactly m characters to make things a little easier. And we now search for a query string. Now the query string can have a different length. Doesn't have to be m. How many nodes in the trie are visited while you're answering this query? And answering this query means, is there a string that has this query as a prefix, or is there a prefix of the query that occurs in the dictionary? It's essentially finding all nodes that could be reached through that. And yeah, if Q was equal to M, it would also mean you find exactly one string, or you find there's no such string. But it's often, think about Q being smaller than M. So you're, I think this is the interesting case. Then you're basically stopping the search early, and there might be many different strings stored in the trie that start with the string Q. Okay. So how many nodes of the trie are visited in this single query? That's the question. And remember, maybe go back to this one. how do you search for a query string? Let's do, I don't know, maybe the example is BB. You walk down the tree following these edges with the appropriate letter. And I assume that you just stop where you get to once you're done with this. I'd like to see a few more votes if possible. We're running a little out of time, so I won't be able to leave this open for much longer. But it probably just means we have to delay the exciting news what suffix trees are for tomorrow. Let me show you the results for now. So here they are. I added lots of possible answers just to make it a little more confusing, maybe, to offer you any possible thing you might have come up with. You see a peak for theta q and also m times log n. So let's try to avoid from people shifting around. But the correct answer is down there, the theta of q. And the reason for that is if you're asking about the number of visited nodes, you're basically asking about the length of the pattern that you query for. If I was to query for BB, what are all the strings in the set that start with BB? I would just walk down B and B, and then basically here I can stop. Now this doesn't exactly tell you which of these strings there are, but there's additional steps that would be needed for finding all these leaves. You could walk around all this tree. That's separate. Maybe the question is a little ill-posed because it doesn't really say what you're doing with the query string. If the question is there any string in the dictionary that starts with this query, I can do it in theta q time. So the precise query here should be for that. All right. Here's another one, because it was so much fun. Same setup. We have a try with n strings, same alphabet and same length. Now I'm asking how big is this try? How many nodes does this try have in the worst case? This means it will depend on the strings that you store. All right. And again, it's probably insightful if I show you the example here. So how many nodes can you have in this try if you have n strings of length m? We're at 10 answers. Now, if we were in a room together, these type of questions would be much more fun because you could do something called think, pair, share. You would discuss this. You would first vote and then discuss with your neighbor and then see if that changed your mind, and then we could take it to the discussion with the entire group. I think the best I can offer with Slido is just the think part. But that's at least something. So we have our almost 25 answers. Yep. Okay. So let me lock in the vote now. And most of you got this right. The answer is n times m. And I'll show you on the example why that's the case. In the worst case, the strings differ very early. So basically what happens is most of the time you have some prefix where it's branching out as a tree. But then the remainder of the strings all look like these linear chains where you just have one node per character. And you need roughly as many nodes as there are letters in all the strings together, because all of these nodes just caters for one letter in one string. Okay. This is also the main weakness of tries. This is why the try in the form that we've just seen it is not really useful, it's not really feasible to use. If your words are very short, maybe it's not a big deal. But again, think of the scale of Google. You can't afford to store 5 times, even if strings were short like 5, you can't really afford to store 5 or 10 times the size of the internet. That's too big for an index. You really want, and this doesn't even store any additional the positions. That's just the number of nodes. So that's just out of the question. This is too much. And we can improve upon this using compact tries. So what are these beasts? The idea is, if you look at the worst case for these tries for the space, you find that these long chains of unary nodes are really the pain, are really the part that that hurt the space, that require many nodes. What we instead do is we compress all paths of unary nodes. So whenever we have 2 such edges, we just make that a single edge, as you can see here. And we do that also here, and you see this just became this edge. Now, we do have a little problem here, because previously these 2 edges were labeled BB. But now we only have space for a single character. Always take the first. That's the rule. But that means we somehow lose information in this process, and we have to fix that. So what we do is we store in the internal nodes the position that we compared. Okay, so in the root we start comparing with the 0th position of the pattern or of the strings in the dictionary. And if we jump down here, it means that the next character we look at is that at position 2. Okay, so this A here is really at position 2, not at position 1. Again, this A is at position 2, not at position 1. That's why we have the 2 here. Okay. What that means is that all nodes have at least 2 children. If they had only 1, we would have removed them. And that means every internal node makes the number of leaves go up by 1. And so it's the same bound we've used before. The number of nodes is at most the number of leaves, and that's the number of strings. So the number of nodes is now order n. Instead of before, remember, we had n times m. That was the space of the standard try, and now the compact try gets this down to order n. So again, starting with the standard try, you find all the paths of unary edges. You only keep the first label, but you have to store in the nodes now a number that tells you how many characters you have to skip, basically. Okay, but formally it's the next position that you compare so that you know what these 2 letters, what they correspond to. If you search in this compact try, you have to make sure that once you're at the leaves, you also check for the skipped characters. So if you were to search for BAB, you would go position 0, I find a B. Position 2, I find a B. Yeah, I found BABB. But hold on, this is BBB. So once you completed the search in a compact try, you have to compare the characters you skipped over, because you never compared the character at position 1 in this search here. Okay, if we use the compact tries we can build an inverted index that is very simple, supports fast lookup, and has not an insane space requirement. It's essentially as big as the number of words, not the total size of the words. The downside is, and this is intrinsic to all the versions of tries, it's restricted. It cannot handle other queries. It cannot possibly search for a substring, a part of a word. It's also not easily doable to search for a sequence of words that have to occur in a certain order. And the main big question is, how do you do inverted indices in situations where there is no notion of words? If you have biological sequences, a DNA strand, there are no words. These are just nucleotides all over, billions of them. How do you search? How do you build an inverted index in that? Or binary streams, if it's just a file, and you'd like to support searching on a lower level. This doesn't work with inverted indices, and you need new ideas for this.